Rafi. So today I'm going to present uh, our paper that has been accepted recently in this year's CPPA 2026. So our paper name is WalkGPT, Grounded Vision Language Conversation with Depth Error Segmentation for Pedestrian Navigation. So these are the all wonderful co-authors. And I have some QR code added here, like one is our project, and one is our lab, and etc. Like if you guys want, you can scan it and go see the project on our lab. So yeah, let's get to it. So as you can guess from the name itself, so we are actually targeting this pedestrian navigation task. So before going into further, like what is pedestrian navigation? So basically, when we are talking about like pedestrian navigation, we're saying like, okay, like given a first person view image coming from a, let's say, camera phone, or more recently from the Google Glass, or any kind of like first person view image coming from a pedestrian himself or herself. And from that image itself, then there should be a navigation guide. Like it should provide a complete accessibility assessment of the path ahead. Let's say, for example, for this image itself, like if I like say walking in this park and itself, then I take a picture and send it to the model. The model should say something about like it's a safe, accessible path with probably there's a bench in front of you, so you need to move around this bench, all those kind of stuff. So this is kind of what we're saying, like pedestrian navigation, which is the main task of our talk. So when we do talk about the pedestrian navigation, we say like, okay, so what a user needs like for this kind of navigation related task. So the first thing is like when the model gives you an assessment to the pedestrian itself. So there are a couple of things that needs to be included in the navigation. So for example, the assessment should have like what are the walkable surfaces, like which of the like let's say features of on the path itself, like how are they accessible or not? Like say for example, sidewalk or paved. These are very accessible. It helps you with your navigation when people walk in the street. Also, there should be a hazard identification, like which are the harmful features. Say, for example, as we saw in the previous slide, when we saw there was like a bench, it could harm a person who has a low vision or like impairment. So then also a good pedestrian navigation should have geometric awareness as well. Like when the model says like, okay, these are the features that the pedestrian needs to be careful about, or these are the some of the good walkable surfaces. But it should know like what are the shapes and the sizes of these features. Then another important part of this would be the distance estimation. Like if we say, okay, there's a curve in front of you, but also the model needs to say how far it is. Is it like 1 meter that the person needs to be careful about it right now, or is it like a 50 meter away? So we don't need to care if even if there's a car 50 meter away, we can just take a detour and just skip that. And all these things should come in a natural interaction, like a natural conversational language, like so the user who is using this kind of navigation, so like gets all of this information in a natural conversational language, so that would help him in his like day-to-day task. So the next slide, yeah, it says like why it matters. So it might makes you wonder like I can see everything in front of me, so why does it matter? So uh, so sometimes routes can like contain this static and dynamic barriers, right? Like stairs, uneven terrains, or temporary obstruction. These are actually challenges. Main challenges are for mobility impaired people that cannot walk freely as other people can. And most of this navigation kind of research work are based on vehicle like smart cars, like when we use Google Maps or Apple Maps, we can see that this kind of navigation guidance or the research are based on vehicles, like for smart cars. And so whenever we see a paper kind of like this, like a smart car navigation itself, so it's based on the streets, or but mostly, but very few of this research are like more focused on the pedestrians path, like when we walk in the sidewalk or the crosswalk, or let's say we're taking a walk in the park. There's no navigation guide for this kind of stuff. So then, then we see a potential solution, like what's a potential solution can be for this kind of pedestrian navigation. So when we say navigation is still just like an explanation of what kind of like a scene description kind of stuff, like what's in front of you. So that's why one of the potential solution is the large vision language models, or the LVLMs we call it for short. So it's just like for you guys know, like if you know LVLMs, the very popular LVLMs are like Lava or QueenVL or Instructive, which are like very popular models. So why these are like a natural solution to this kind of research question? Because since large vision language models are what, like it's LLMs on top of a vision encoder. So it's like LLMs with a like a with the eyes that can see. So in very high level understanding. So since these LVLMs have like hybrid architecture, and it can process with multimodal inputs, like it process images, text question simultaneously to generate answer. So and since these are like trained on massive image data set, so if we ask a simple question, it has the potential to answer some simple question like, can you explain the scene in front of me? That's kind of thing these large vision language models are really good at. So yeah, like why it's a good fit. Like I think I have already went through like scene reasoning, right? So these large vision language have models have very strong ability to describe and reason about the complex visual scenes, and they can take open-ended question. Like it's not like fixed question all the time. So it can take a flexible question like what's in front of me, what why will it fail, or something like that. So different kind of questions, and the interaction itself with the user and the model is very natural. Like it's kind of like a conversational responses back and forth. Then we kind of go deep into like why. So we first say like, okay, LVLMs is a good fit, but the current LVLMs or the large vision language model, why they are not actually a good fit for the pedestrian navigation. Like it's a very good explanation of a scene for a general category, but for pedestrian navigation, they might not be the best case out there, like best solution. So why? The first one is no geometric understanding. So when you're saying like when no geometric understanding, so when we ask a question to this kind of large feature language model, so we ask a question, the model gives an answer in text based on the question and the provided image, or let's say video itself, let's say a visual in. But this current large vision language model doesn't have any geometric. No, it's like it doesn't provide any geometric output. Let's say it cannot segment or delineate the shape on the boundaries of the state features. Like it can say, okay, there is a curve or like a bench in front of you, but it does not say, or it does cannot provide like exactly where the bench or the exactly what the shape of the bench is. It is. And also like for long elongated structures like sidewalk. Let's say there's a sidewalk ahead of you, but this model will not tell you exactly where the sidewalk ends or the obstacle begins. Uh, these models have not been trained for depth estimation mostly because this is a much harder task. Like depth is estimation, which falls in the spatial reasoning part of the large vision language model. So in generic, like in zero shot settings, these models cannot estimate like how far away a vehicle, a car, or obstacle is. Like it, the current approaches and also this current approaches that have been done only rely on like user provided visual cues. So what I mean here, let's say if the user gives a point, like, okay, there is an accessible feature like a sidewalk or harmful feature like a dog on the street, it provides a visual point on the image itself, then the model can gives a good estimation. But that's impractical in this case because the user is asking the question, so it doesn't know where the features are. So in a perfect world, the user just needs to ask a question, gives an image, and everything will be provided to the user without any further inputs. And one other thing which is very common in this kind of lava-based models is hallucination. So when we ask a question on these models, the models kind of overall it can perform good, but it provides some hallucinations. Like the responses are not grounded in the actual image content. So what it means, like the response from the model will have some information, like some features that are actually not in the image itself, because these responses are not grounded to the features. Like when I say not grounded, like the sometimes the features appear in the conversation that are not in the scene, but that's where we say it's not grounded. Like if the features that appear in the scenes sorry if the features appear in the responses of the model itself, and also we can see the segmentation of the features, then it's much more grounded. Like model cannot generate something out of air. Like it cannot generate a segmentation map, which is much more harder visual task. So yeah, as I was saying, these are the summary. Like the current LVLMs, like they don't have this kind of like segmentation output. They don't cannot do the depth estimation, and since the responses are not grounded, so they do sometimes hallucinate. Yeah. So then, like how we solve it, like our main point of our main part of our presentation today. So we introduce WalkGPT. So let's just see this one single input output from the model itself. So let's say this is our like a given input image from the user himself, uh, park kind of settings. So then the user can provide some question like, can you describe the path in terms of accessibility for a pedestrian? So like, and including segmentation mask for accessible and harmful features. So this is the question. This is the question, and this is the input image. Then the model will provide the assessment, like in the path appears largely walkable with a smooth paved path, etc., etc., etc. After that assessment, the model will also provide a list like, okay, here are the accessible features are the sidewalk, paved, and the non-accessible features, or say the harmful features are tree, vegetation, building, vehicles, and obstacles. So this list, as you can see, the color itself, so it's for basically for visualization purpose, but it's saying it's what it's illustrating that whenever the model provides this kind of features, like accessible and non-accessible features, the model is also generating a segmentation map for these kind of features. Like whenever we say sidewalk, we can see the sidewalk, the segmentation map of the sidewalk. When you see the obstacles, the model also provides the segmentation map of the obstacles as well. So at this point, like the model is giving a complete assessment. It's saying, okay, here are the accessible features, here are the non-accessible features, and the shape of the accessible and non-accessible features. But that's not enough, right? Like so, since it's a 2D image, so uh, a user might say like, okay, there is a tree or there is obstacle. So, but how far are they? Like, since it's a 2D image, so only the shape is not like the shape itself is the shape of the simulation map is not enough. So that's why we also introduced the distance or the depth estimation in the generated output of the model itself. So whenever the model provides all this in the natural language region, whichever the features the model has uh, outputted in the generation, it's gonna calculate the distance, like an estimated distance from the user himself. So let's say, for example, for the tree, 1.2 meter, or the building far away, 50 meters, that kind of thing. So these are not like exactly perfect distance, but this gives the user a very good estimation of how far the features are. So whenever the user says, okay, the model is saying, okay, there's a tree in front of me, I know exactly the shape where it is and how far it is. So the user knows how to avoid it. Or let's say if it's an external features like sidewalk or pastel, then the user knows, the pedestrian knows how to access this sidewalk and where it starts from. So yeah, that's basically our model, like in a very high level stuff, like user asking a question and the responses includes assessment and everything, and also the segmentation maps as well. So the input is question, image, and the output is the text itself, the generation coming from the generative AI model, and also the segmentation mask. So our WalkGPT model. So this the technical contribution. So this slide is basically for the what of the technical contribution our model has provided. So first one, we use one single visual encoder to do two tasks. So we have two main tasks. One is the segmentation itself, and another one is the language generation. So we use a one single SAM VAT encoder to do this both language generation and segmentation in this model. So then we have two novel architectural modules. So both are different kind of projectors. So we're going to go into details in the further presentation. So basically, they're like better projectors suited for this kind of pedestrian task. And we have a region alignment loss, which improves in very high level understanding, it improves um, the language and the vision part. Like whenever the language part connects with the vision part, it improves the connection understanding. So we're going to go into detail. So I'm going to tell this in much detail in the next couple of slides. And this work, our model has been trained autoregressively, and it does the object level distance through the cross entropy loss. And finally, we also introduce some of the structure tokens, like assessment tokens, the paragraph tokens, segment tokens, like the seg tokens, distance tokens, all these tokens, so that these structure tokens kind of like links everything to one single forward pass when we do the training of the model. Yeah, as I said, like I'll go into details of each of this. So this is the big figure from the paper itself. So like it has like a couple of section, like A, B, C. Like the A is the our like overall framework. The B is the what the projectors are, like just I said, like MSQP and the CTP and the regional alignment laws. So if you guys bear with me, I'm gonna go into like one by one all of them. So at first, this is the overall outlook of our full work. So first thing, yeah, the A, the WalkGPT overall framework. So as we seen before, like the user asks a question, like the question input, with a given image itself, like an image where the pedestrian is using. Let's say, for example, this image, the user is crossing the intersection. The user or the pedestrian is using this crosswalk. So the visual input here is the image. The question input here, like, can you describe this part in terms of accessibility? So this question like it goes through like a tokenizer. It creates text tokens. It goes into this LLM, which is the backbone of our large vision language model. Then this visual input goes through this pixel encoder, the one that we just said, like we use one single pixel visual encoder or pixel encoder. So it goes into this pixel encoder, it creates the encoder embedding. So the embeddings coming from the pixel encoder, which goes into our MSQP, which is a projector. So like one of the modules that I talked about in the last slide. And this MSQP creates these image tokens and goes into the large language model. So the model takes image tokens, the text tokens, it does its magic in between large language model and generates this output tokens, right? So the output tokens, then the output tokens um, are projected into natural language responses. So you can see from the output tokens, we are generating this full generated answer, like the one that we saw in our first figure. And everything has been done within using the structured tokens. So these structured tokens make sure like the model generates kind of like in a structured manner. So it kind of forces the model to provide all the things that we want, like in a very structured way. Let's say, for example, the assessment token itself. So assessment inside the assessment tokens, the model will provide general assessment of everything. Then after the assessment tokens, the model will list the accessible and the potential harmful features. And each of these features we are like enclosed within this P and P tokens, right? So these P tokens are the paragraph tokens, and immediately after that, then we have the sec tokens itself. So it's kind of grounding the conversation. So whenever the features are presented within these P tokens, they are grounded. Like if every time a crosswalk is so, let's say for example, every time the crosswalk, not every time. Let's say the model has generated this crosswalk within this P token. So it has been enclosed and it generates these sec tokens, and these sec tokens will be used to create the segmentation mask itself. So the model will have to generate this crosswalk within the generated answer and the segmentation map it's at the same time. So, and we also have the distance tokens where the same feature that the model has explained will provide the distance as well. So as I was saying, so these output tokens will have these sec tokens. So only the sec tokens will be extracted, like the hidden states of the sec tokens itself, because all of these sec tokens have the information, like it kind of has the summarized information when it's like it's present after the crosswalk or other features. So yeah, when the sec tokens, each of the sec tokens is generated after each of the features, right? So these hidden states will be extracted from the output tokens. And since they have the information, like where was the crosswalk or where was the sidewalk, so they kind of like work as like a segmentation prompt for like a SAM-based model, segmentation anything model. So this then goes into the CTP, which is another projector that projects into the visual space in the pixel decoder. And this CTP was also trained through through this regional element law, so that it improves the projection itself. Then the pixel decoder generates for each of the sec tokens, it generates each of the segmentation mask in the scene of the given image. So that's the overall framework. I'm going to go into details of each of the components after, but basically that's the overall framework. Like one visual input, one question input goes into the LVLM, then it generates the output tokens, and among the output tokens, it has the sec tokens of each of the features that we care about, the related features. And this features goes into the pixel space, and then it creates the segmentation mask. So the output has both the generated answers and the segmentation mask of all the features in the model. Okay, so then we can talk about like what the MSQP is. Like if we go before in the framework, we can see the visual input of the image goes to the pixel encoder. It gives us the encoder embeddings, and the MSQP is turning those into image tokens. So now we're going to see like what is this MSQP, or we'll say multi-scale query projector. So it's basically very high level wise. So this, let's say, most of the this kind of LVLMs just use a linear projection to do the this kind of projection. But in our WalkGPT, what we have done is that we asked the model to like see the encoder embeddings in couple of zoom levels. Like instead of just one single zoom levels, we do multi-scale. Uh, okay, let me go over this figure. Like encoder embeddings goes into this some linear projection, then we do like multi-scale, so it's like zooming in different scales, and we have some seg aware that is just MLP layers to like kind of like focusing more on the important stuff. And we have this learnable queries that cross attend of each of these scales. So and then at the end we do the concatenation and we get the learnable queries, like the full learnable queries that works as the image tokens that goes into the model. So basically, these learnable queries are the one that is the MSQP is generating. So what it does that we take these learnable queries and number like a specific numbers. Then we use some of it for scale one, some of it for scale two, some of it scale three, some of it for scale four. Then these learnable queries have information of the visual understanding of the scenery in multi-scales, which gives the model much more understanding of the scene, right? So then when we ask questions, like very questions that needs much more fine-grained understanding, including the distance itself. So this improves the overall performance of the visual part of the model itself. So that's basically what the MSQP is doing. Like it's matching the SAM pixel encoder embeddings into the semantic aligned image tokens. We do four spatial scales as like four zoom levels kind of thing, and each scale is modulated by the segmentation-aware gated function. And we do like two layers of cross attention for the query embeddings. And at the end, like the outputs are concatenated and projected into the LLM's hidden space. So that's the first component. Then we have the calibrated text projector CTP. So let us go back to the overall framework again. So when we extract the sec tokens, uh, so these sec tokens are very high dimensional stuff, like 4096 for lava. And the pixel space, the visual space, like in especially in SAM, they work with like very compared to that very low dimensional, like very 256. So what we're basically saying, okay, we have this so token, so hidden states are just like vectors, right? So they have like high dimensional vectors from almost close to 5K, and we're converting them to 256. So obviously there will be a, a loss, like a huge loss, and most of this works. What they do that they just use a linear projection. So we improve that with this CTP. Like we're saying, okay, it's not gonna be just linear projection, but we're gonna kind of like create this into multiple banks. So what does it mean? So standard linear CTP, like the one that we just said. So what it does that it expands each sec token hidden. So when it says sec tokens like this, so it just like each of the sec token is like just a vector, the hidden states representation coming from the model, the LLM itself. So each of these sec tokens are expanded into K bank, and so they are expanded, and each of the sub embeddings kind of like a capture a different complementary aspect of the token semantics. Then we do some reshaping and concatenation, and then we map to it. So instead of just one single vector, we do like we are basically expanding into multiple banks, and so then at the end we do the concatenation. So the model gets more information. So so the loss, there's still, it's obviously there's not like we're not keeping everything like from 1496 to 256 dimension reduction, but it improves the performance like when we keep more information. Then the next question comes like what the region alignment loss does. So basically, like when we are converting from this 1496 to 256, right? So we're still reducing a lot. So we make sure this region alignment loss that when this projection happens, so this since these sec tokens work as prompts, right? Like if you guys know what SAM does, is that if we provide a visual prompt, let's say we say to SAM like, okay, segment here, kind of like a approximation of the place that we need to do the segmentation. So we're making sure like when we do this projection and work, these sec tokens work as text prompts in the SAM, we make sure the correct region has been pointed out from this projection itself. That's where the region alignment loss comes. So what does it mean? The region alignment loss. So when we are projecting everything through CTP, we make sure we do some supervised learning through this region alignment loss. What is what is this? That is just some like info NAC loss that it makes sure that the map sec tokens are pointing to the right region of the model itself. Like it supervises CTP projection to ensure the map embeddings remain faithful. And how does it do? Because we actually use the cross attention to identify the most relevant spatial areas as pseudo targets. Like each of the sec tokens that we generated, it knows where the correct portion of the visual images are. So we use those we sorry, this one. Yeah, we use those most relevant spatial areas as pseudo targets, and we do some like a contrastive loss kind of function, contrastive loss to improve the overall projection. Yeah, so that's the overall framework and in explaining everything. So then we talk about our next contribution, the PAVE dataset. So since you guys have seen, like we have so many structured tokens and everything, and this image, including the segmentation mask. So there wasn't any data set that we could have used to train our model because we introduced so many new things. So then we created this 41K image question answer pair, we're calling it the PAVE dataset. We take some real pedestrian view images from Sanpo dataset, and these are like a real captured images, including with segmentation map. And we use those images and segmentation map, and we use like another LLM to create this question answer pair. So how do we create this? So let's say we get this input image from this image data, so real image data. So we provide the image, the system prompt, whatever the features present coming from the original image source, the distance of the feature. So distances. So those real images, the main image source had the depth map, like pixel wise depth map. So from there, we calculate the minimum distance, like what is the closest pixel that's closest to the pedestrian himself. So we calculate that distance of those features. So these are like object level distance. So as I was saying, like we give the, let's say in an LLM these features, the distance of the features and accessibility of the features. Accessibility means like, okay, I have this features sidewalk. Is it like accessible or harmful feature? So we give all this and then we ask the LLM to generate the question answer to pair. So can we describe the paths in terms of accessibility, including a blah, 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 blah. Then we get this whole thing. So this is the pipeline on how we created the data set. So we took real images from this Google Research Group sample images, and we created everything, including the structured tokens that are needed to train our model. So now we have everything: the image, the question, the answer, including the assessment, including the structured tokens, and we can train our model. And we also publish this dataset as a public dataset so the research community can use it further. So for the training recipe, as I said, like we use the LLM training to auto-regressively to do everything. And each seg token is extracted, mapped by CTP to create the segmentation map. And this depth estimation, like the distance, we do it within the cross entropy loss, like within the text generation. We don't do anything other, like we have this depth estimation head or something, because these are like more like an object level distance, like a single token, and these are generated within the generated text. So experiment setup. So I'm gonna skip this. You guys can see the code for further details. Okay, so now we have some quantitative results. So when we do the quantitative results against the other state-of-the-art model, we took grounded large decision language model, like the models that can also do the segmentation and the conversation at the same time. So we first see one important thing, like the zero shot of the using zero shot under performance of each of this model is really bad in our the dataset that we just talked about, the PAVE dataset. And this shows that why it's not like it's has a hard task to do this kind of pedestrian navigation. And in the quantitative result, we evaluated against three different metrics, like text generation, how good the quality of the text is, how good the segmentation performance is, and how good the depth estimation is. And even with the fine-tuned version of each of this model, they perform a bit at that level, but our model in both 7 billion and 13 billion performs really good, like better than all these models, because of those the newer modules, the novel modules that we talked about, MSQP, CTP, and etc. Some qualitative results, like we show that it's different scenarios, the data set has different scenarios, different people, and different kind of questions. And as we saw before, like it gives a assessment and distance and segmentation mask. These are for visual purposes, like segmentation mask are, are drawn over the input image. And we do some further analysis, like since we check how good the segmentation performance is against only segmentation only model. So we can say that our model is not the best compared to only segmentation only models, but it's the performance of the segmentation is close to that. And one other thing we also talked about, like it improves hallucination itself. So we also compared against some basic large vision language model like Lava or Wayne, and we found out that the the hallucination is much it does less hallucination compared to this kind of large vision language model, due to basically to the grounded conversation generation. And we do some ablation study. Due to time, I'm gonna skip this. The summary of it is like when we every component contributes, like no single part is generated. If we take out one of the part, the performance drops. So one of the limitation is that the models some like we showed one example, like when the reflection is really good. So let's say, for example, the building reflection, the model gets confused. He thinks the model thinks the reflection itself is the path itself, like the path in front. So, like for example, this image, the car in the road is not actually in front of the pedestrian. It's a reflection that's coming from the car from the path. So the model gets confused and it tries to say, okay, there is the car is the segmentation, like this is the obstacles, and the assessment also gives us bad assessment, like the presence of cars, various obstacles, and active road traffic. This makes the pedestrian the road challenging, but which is not. So that's like one of the failure case. It mainly because of the model has doesn't have that spatial reasoning capabilities, and since we use single view images, like one single view, and doesn't have this 3D understanding, so there are some still evident failure cases. Yeah. So to conclusion, like we introduced grounded vision language conversation for the pedestrian navigation. and it links guidance with segmentation mask and object level destination distance estimation. We also released the PAVE benchmark that we just talked about, 41K samples for like further research on this topic, and we showed some strong empirical results overall, including three different categories. Um, yeah, that's it for my presentation. Thank you. Yeah, yeah, Mike. Mike, it's up to you.
Yeah, thanks for the awesome presentation. Uh, there were a couple of questions in the chat. Uh, I think Benedict, can you go ahead with your quick query here?
Okay, thank you very much. Um, Hi, Rafi. Thanks for taking the time to be with us today and sharing your work. It's very interesting work. Um, I didn't really have much questions. I really got everything you were saying. I understood practically what you were saying. So yeah, thank you very much for the good explanations and all. I just have one question really. So for the MSQP component, we we actually split the encoder embeddings into four scales. We try to process it at four different scales. I am aware from the paper and also from your explanation here that you make use of a segmentation aware getting function to modulate your embeddings at the different scales. But I don't really know if you can help us
So
with a bit of
yeah, yeah. Thank you, Benedict. So basically, these Segware gates are like MLP layers. So it's a fancy term for Segware gate, but these are very simple MLP layers, and like these learnable queries through cross attention. Like when we get this one different scale and it goes through this MLP, let's say one small MLP network, and this learnable queries through the cross attention, it learns the different scales. So this part learns one scale part, and this part another scale part, and then at the end when we do the concatenation, it has like a concatenated understanding of different scales. But to answer your question, yeah, these are like very simple MLP layers, nothing so fancy. But if you want to check it out, we have the code. You can see for yourself. Yeah.
okay. Thank you very much. Because
Mhm. Yeah. Thank.
when I saw that they about the segmentation aware getting function, I was thinking, okay, it is that this is something fancy that I have not seen before, or B, it's probably something like a can each function or a softmax or a can each function like what we used to use for gated recurrent units back then and LSTMs. Yeah. So I also okay, I will try to make sure I ask that question on the video. So
Mhm.
thank you very much for the answer.
Yeah. Thank you, Benedict. Yeah.
Yeah.
The next, I would like to probe a level deeper with respect to uh, the dimensions of it, since like the working dimensions you say here it's 10224, and I think so. Uh, the it is divided into uh, the layer normalization layer, which kind of segregates into
Mhm.
scale 1, scale 2, scale 3, and scale 4. So, do you have some sort of router that is like this LN layer that selects one scale, or like you kind of concatenate the SPAD after each and every step here?
So no, I kind of I didn't understand the question. So a router. So
A
if there's.
router in the sense of MOE layer, like if you like I go to a mixture of experts in
Okay.
that we kind of have a router in which you have certain experts, and your main uh,
Okay.
projection there
Yeah.
goes through that. So I was thinking
Mhm.
from that perspective, and
Yeah. Understood your question now. Okay, so no, there's no. So at the encoder embeddings itself, right? They come in from the SAM, so they're like 256. So the linear, this linear projection kind of uh, project it into 1024, the working dimension, as I said. Then we do the pooling to get this different scale understanding. Then we do the concatenation with this all these learnable queries. So it's much more simpler than you are thinking of. Like there's no expert or anything. Yeah.
Cool. So, like, do you also have a problem of having the dimensions that is scaled, since like you are only training on one H100? So, like, if you want to have multiple GPUs there, so will this be scalable across, or shardable, or like, can we do that?
Um, yeah. So if I understand your question correctly, like if we make it more complicated, right? Like and use like say another H100. Yeah, of course. Then we can have much more complicated design. But then the issue would be like the training would be much more slower. So yeah, that is possible. Like let's say, yeah, obviously you saw the problem, right? Like when we do the projection, we lose some information there, but it's kind of like a work away to improve over the existing just linear projection. So this gives the model much more scaled understanding of the visual image. But I do agree with you. Like if we have a much more complicated, or let's say much more fancy network, that would improve performance. But again, that would take a much more computational efficiency.
True. Harsha, you can go ahead with the question.
Sir. Thank you so much. Uh, Rafi sir, it was really great paper. I did my ME in computer science engineering with AI/ML, and I'm actually trying. It's very general question. Like I'm actually trying for PhD in computer science or data science. So I have published some 5+ AI/ML research papers in Tech Archive, like Spaces. So how can we select the journals that are that doesn't have I mean doesn't have a processing phases, suppose Scopus index, to get an edge with the selection process? So it's very general. That's why I I'm asking it at loss. So what are your take on it?
Yeah, that's actually a excellent question. Yeah, so uh, for our lab, we actually mainly try to publish in top AI conferences. So it's not like we don't like journals or anything, but journals are kind of like takes time to do everything. Like when you submit and it gets published, it takes like sometimes it takes even 1 year. So we do submit to this like top AI conference like CVP and UDIs, all this kind of stuff. So my suggestion would be you can also try this if travel isn't an issue, because submission is all of these conferences free, and we get like even if our papers get rejected, we get some very good reviewer comments within a 1 month or 1.5 months, so that can improve the paper. So, and for the journals, I'm not that much sure because we typically don't submit to journals.
Okay, sir. Yes, sir. It was amazing. Yeah. Thank you so much.
Thank you for your question. Yes.
Cool. So, like, I would like to ask about the SAM. Like you have used here uh, uh, SAM. So this is the first, I think so, the first version.
Yeah. It's a
Yeah.
SAM, the first version. Yes.
Did you elaborate, or do you plan to experiment with the second and the third version, or the 3.1 that came out recently that had improved like matrices across the board?
Yes, SAM 3 would be a much improved. I think SAM 3 would be a much improved version of the SAM 1. So when we did this work, we only had SAM 1 and SAM 2.
Mm-hmm.
SAM 2 was basically for, as far as I remember, it's for videos like temporal image frames. But SAM 3, I think it would improve performance because SAM 3 was trained for this kind of like text prompts, right?
Mm-hmm.
So right now we don't have any plans to experiment with this SAM 3, but that's a very good, interesting direction. I haven't thought about it, so maybe I will try in a later part. Yeah,
Mm-hmm.
but right now, what I'm working on that improving overall spatial reasoning of these large vision language models, which is also very interesting task itself. Like we had one of the very smaller spatial reasoning task, the distance estimation, but the overall spatial reasoning is a much harder task. So that's what we're working on right
Yeah, spatial reasoning can be very hard, specifically
now.
when you have the pedestrians and the sidewalks and the buildings that kind of reflect. So
Hmm.
that can be a difficult scene to uh,
Hmm. It's a
segment
very
and yeah.
it's a very hard topic, yeah, like it's a very
Mhm.
hard topic doing, like if you see some recent manuscripts from CVPR and ICLEAR 2026, a lot of people are doing just improving spatial reasoning
Mhm.
in large vision language models.
Yep. Benedict, go ahead.
Yeah. Before I talk about what came to my mind, I was hearing you guys talking about the spatial reason thing, and I will admit that I'm not very well versed in that sphere of knowledge. Uh, but I was just thinking about something now. The idea of temporal graph computation, right? Maybe you use temporal graphs, basically graphs that change over time. Do you think perhaps that might make it easier for us to perform spatial reasoning?
Yeah, it depends on like what kind of spatial reasoning task you are referring to. Let's say it's the task, like the question itself can be answered on multiple frames. Say for example, the question is, okay, if the boy throws a ball, like how far the ball will travel until it hits the ground. So this kind of question needs, when we need to answer this kind of question, right, we need multiple frames. Like we don't need multiple, we it will help the model if we have multiple frames. Then I think your point will be important. Like if we want to answer a question based on multiple frames, like one frame the boy is throwing the ball, another frame the ball is going through the air. So I think those kind of question, this kind of like temporal graph will improve the spatial reasoning for this kind of models. But our like this paper in our model, we only work with one single frame.
Fair enough. Fair enough. Thank you. Yeah. So the second question I wanted to ask was so the idea of WalkGPT right now is we want to bring up a solution that is useful to pedestrians because most solutions in the space focus on smart vehicles and stuff.
Mhm.
One of the more important factors that would influence how useful it would be to pedestrians would be how easy it is to deploy. So, for instance, if it's a very large model that's difficult to deploy on most consumer hardware, then most people would not be able to make use of it. And even those who can make use of it will probably not be able to make use of it for long, right? Because it will end up consuming a lot of power. So, have you guys thought about that aspect of the project?
Yeah, so that's a very good question. Actually, one of the reviewers also asked it. So at that point in the future, we haven't like thought about, like if we want to deploy this on a smartphone, right, like we need to think of like other techniques, like say we do knowledge distillation kind of stuff, or let's say we run we deploy this model in the cloud, then we just ask the question and we get the answer. So those are some like interesting future directions that we can think of, like if you want to deploy into smart devices like the glass or the phone. But that part we haven't addressed yet in this paper. But that's for the future work. Yes.
Yeah, sure. I know that you guys didn't address that in the paper. I was just trying to understand if at least there are plans or something like that, and if already
Yeah.
laid
We
out there.
actually so we actually have plans because this is part of like in it's an NIH grant, so that's like that's that works on this like to deploy on a like a smart device. So this is kind of like the first part of that grant. Like we have we have found what's the like issue and how to solve it. Now the second part would be to make it much more convenient for the users.
Fair enough. Yeah. Thank you very much.
Yeah, thank you, Benedict. Yeah, for the questions.
Yeah.
Yes.
Thank you. With that, I think so. We will call it a call, and we'll end our presentation here. Thanks, Rafi, for your excellent presentation.
Thank you, Mike,
Uh,
and go ahead like for giving me this platform to present my work.
Yeah. Thank you very much, Rafi.
Yeah, thank.
In case anyone has questions, you should be able to reach Rafi on our Discord channel.
Yeah, of course.
Yeah.
Yes, yeah.
So what's your username again?
Yeah,
The username on Discord.
yeah. I just
Yeah,
I joined the Discord. Yeah, and also you can email me on LinkedIn anywhere you want. Yeah, I'm available.
Okay. Thank you very much.
Yeah,
Take care and have a nice day.
yeah.
Bye, everyone.
You too.
bye.
Yeah, then bye everyone.